Good afternoon, everyone. Going to do a little demonstration of try and understand what might have gone wrong with the demolition. I'm sure you recognise what that is. That's the broken off end of the building. And this is Unit 3. Unit 4 is there, it's not shown. Unit 2 is there. Now this enormous top frame, the boilers, hang from the roof of the structure, and they hang from this top frame. It's actually called the top steel, and it appears to have come loose from losing its connection with the column at the back there. It's come loose, and it's managed to wiggle its way off the end, and it's come down like this, flattening everything under it. Took the legs out on Unit 1, which was over here, and then Unit 1 came down, and the back corner of Unit 1's top steel ended up over the back corner of Unit 2. It was rested across like that. So this fell first. Let's put it back on Unit 3. And incidentally, it was only connected at the centre. There was a resting joint at the back and at the front. The beam wasn't actually connected to the column. That was to allow for huge temperature changes, expansion and contraction. And the beam at the end actually rested on a pad. And so beam's going across here, and it's rested on that pad. And the idea is that the column can rock backwards and forwards very slightly. It actually flex, and the beam could kind of rock on the pad. Now, interestingly, this actually used to go on there because it went like that way, sorry. This is the middle column, and that was originally attached to the beam. It was the end column that had the pad on it. Now, what's happened is the middle column, when they finally blew up the building properly, it not only had been cut away at the top, they'd actually pre-weakened it. And when the building was demolished, it just came apart because they'd cut around it. Now, that's absolutely fine. That worked well. That was fine. What they did at the end, I don't really understand this, because that does go that way, is that they cut down the sides of the column. Let me just peg that on there. They cut down the sides of the column. They went that way, like that. Let's pan back a bit. They cut down the sides, across the bottom, and back up the other side. And I'm guessing, given the symmetrical nature of the failure, that they did at least something similar on the side you can't see. Now, when you look at the wreckage, what you're looking at, let me fake this to demonstrate. Let's as the building has failed, this has come across like that. It has flexed like that. That weld there has broken. So let's disconnect it. That weld has broken. And this plate has gone in. I'm making a meal of this, aren't I? This plate has gone in like that. Oh, I'm trying to do it one-handed. That plate has gone in like that, and the top has bent over it like that. So what you're looking at in the pictures is something like that. And these are right round like that, but that's basically what's happened. That's right round like that, and this is right over like that, and the top there is like that, and you can actually see that pad. Now, it's not a very nice Difficult doing things one-handed. I'll put it back together. Now I want to show you something. These plates, they're flexible. See how flexible that is? Not a lot of strength in that. Yet, here's something remarkable. Let me show you something. Let me show you something. Let me show you something. And get to stay the camera. I'll get on this. That thumping you could hear was me lifting my feet up off the ground, putting it back down again. Now, I'm 17 stone. That took 17 stone. Remember, it's in 2 halves, and it's made of the same flexible plastic as this one. Now, because they cut round the 2 end plates, they weren't serving any structural purpose. So what you actually had, let me put this together one-handed. What you actually had was structurally was actually that. Now, yeah, what you actually had structurally was that. Now, it's possible that when the designers worked out the amount of strength they could take out, they were thinking in terms of it pushing straight down. The problem is, not that it's lacking strength straight down. I'm pushing as hard as I can. I can't collapse it. But what's happening is that it really wants to go sideways. I'm actually having to work at holding it steady. It really wants to go. The truth is, it has no lateral stability. Now remember, those were welds, and those welds were simply there to tap the top plate on under compression. They weren't designed to take enormous bending loads. So that has no lateral stability. And that is this here. This single, rather flimsy strut is a very cartoonish, abstract kind of representation of the real building, and that is that, and that has in effect pinged out from under the top steel, and it has gone that way. Now it all feels a bit clumsy doing it one-handed, but and actually that's a loose plate that I hid inside that one to show that they really are very floppy. And yet, amazingly, when you put plates into a square, they get incredibly strong. I actually have another video demonstrating the principle of the Sydney Harbour Bridge behind me that I made on holiday in Australia, and it's worth watching. It's a bit more polished than this one, and YouTube are taking down certain enhancement tools, so I'm trying to rush this video out for tonight to get it uploaded so I can use their creator studio before they turn it off at midnight, and that's why I finally got around to making this video. Now, I've done it in one hand in one take, but the point is, the flex in that is just ridiculous. It's actually frightening to actually sit here and to put a little bit of pressure on that, and it just wants to go sideways. It just wants to go sideways. Now, I don't speculate, etc., 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 but when this top steel fell, it ended up like there. It ended up over there. It went that way. And the end of it, this end of it, came over the column that was underneath it. So as it's fallen, it's ripped all the side braces off the columns. I think the back column got trapped underneath it, but the front column, this one, on the other side, there was a column here, roughly, where the building is. As this has come down, it stripped all the side braces off it, and the column, which is actually several sections bolted together, the top section of the column, the top part of it, has come up through the roof of the building where the bolts are broken, and it's fallen down. And if you look at the pictures of the wreckage, there's a beam. Let's make it longer. There's a beam, and it's scale length. It's like that. It's like that. Imagine that's one beam, and imagine that's one beam, one continuous beam, and it's sat on top of the wreckage. And if you actually see aerial pictures, you can just see this column sat on top of the wreckage. And because what's happened is that as this has come towards it, it is kind of, it sat there, the top steel has slid this way, so the column has gone underneath it like that, and it's come up somewhere between, now let's doing this one-handed again, as the top steel has come down, the column has punched its way through it like that, broken off, all the side braces have pinged off it, and it's gone crash. It's landed on top of the roof like that. It was just quite dramatic. So that's the real lesson here. That's quite a lesson. Now, it's worth remembering the building's very long, and they dealt with expansion and contraction from front to back by allowing the ends to ride on the columns. Only the middle was secured. However, lengthwise, across the whole length of the building, there were no expansion joints. The building simply relied on the strength and the flexibility of the frame. You see that? I can wobble it slightly. That ability to flex slightly and still remain strong is how the building would have coped with changes in temperature. And those changes in temperature would have been very large. When the boilers were on, the temperature up there could get close to 100 degrees centigrade, boiling point. And in the middle of winter, with the boilers off, it could go below zero. So the temperature swing is huge. And on a building that's roughly a quarter of a mile or so long, the movement at the top must have been quite significant. Therefore, it's not unreasonable to assume that because there was this movement, that there were significant stresses pulling. Because when the building expands, when these top steels get hot and expand, they would want to push that way as they get bigger. As they get smaller, they want to pull this way. So the whole top of the building, all of these connected together in a row, would shrink slightly, so there'd be a tension on it. And unreasonable to possibly suspect that tension contributed to this thing coming off the uprights. And of course, once it got loose and it started on its way down, there was nothing stopping it, because all the strength would have instantly gone. Once it let go, there was nothing holding that up. It just went poof, like free fall, like the top of the Twin Towers. So there you have it. Just for the record, see that little thing there? That was where my workshop was. In the actual station, I spent 10 years based in a little workshop between units 2 and 3. And so, and so there you have it. My little kind of explaining of what happened in the, or rather how the station works, how the building works, and how it might have not worked that day it came apart. So just by 2 pennies worth, and that's it. Yeah, put it all back together. So folks, there you have it, and cheers then. Bye.